So I like this example. It's actually problem number 2 on page 253. It's a really good example because it's a continuous function. It has areas on the graph where you'd see the function is increasing, decreasing. There's a part where it's concave up, concave down, and we'll have an inflection point in there as well. So let's go ahead and get started. This is kind of start to finish. How do we analyze a function and find all these things about the function based on calculus? And if we want to know when a function is increasing and decreasing, we first have to find the derivative. This is a good example too, because we can remind ourselves how to find the derivative of a quotient. And so the derivative is the low d high, high d low. X squared plus 1, that's the low. D high is 1 minus the high, x, times the derivative of the low. So low d high minus high d low, and the d low is 2x, all over low squared. X squared plus 1 squared. Equals, so let's simplify the numerator. X squared plus 1 minus 2x squared, all over x squared plus 1 squared. And that is equal to, let's say, 1 minus x squared. 1 minus x squared, all over x squared plus 1 squared. One thing I didn't mention that I'll mention now is that we know the domain is all real numbers because this denominator, x squared plus 1, can only be as low as 1. If x is 0, then the denominator has a value of 1. And if the denominator, or if x is any positive or negative number, squaring a positive or negative number is, and adding it to 1 will also make that a positive number. So the denominator is always positive. Y will always exist. The domain is all real numbers. The domain, just because the denominator is positive doesn't mean the domain is all real numbers, but in this case, it's a rational function, and therefore every rational function that has a denominator that will always be positive will always have a domain of all real numbers. So this is a good thing. So we know we don't have any breaks in the graph. We can focus on what the derivative is and when the derivative is positive and negative, and so on. So let's simplify the numerator again. The denominator of the derivative will always be a positive number, and therefore the derivative equaling 0 will only occur when the numerator is 0. So let's simplify the numerator, and let's write 1 plus x and 1 minus x all over that x squared plus 1 squared. And so y prime equals 0 only when x is equal to 1 or x is equal to negative 1. And so we're going to set up our y prime test. And the y prime test will determine where the function is increasing and decreasing. So we have negative 1 and we have positive 1. And to the left of negative 1. So let's take negative 10. Negative 10, the first factor is negative. The second factor is positive. The denominator is always going to be positive. So we have negative. So the derivative of this function is negative from negative infinity all the way to negative 1. Therefore, the function y will be decreasing all the way to negative 1. All right. And then in between negative 1 and 1, we can take a test value of 0. Put a 0 in there. We get 1 plus 0 times 1 minus 0. Both of the factors in the numerator are positive. Denominator is positive. So we have the interval between negative 1 and 1. The function y is increasing. And then when x is greater than 1, we have 1 plus x is positive, 1 minus a number bigger than 1, 1 minus 10, that's a negative number. Divided by that denominator, it's always positive. And that, therefore, the derivative is always negative from 1 to infinity. The derivative is negative, therefore the function y is decreasing. And that takes care of knowing that we have a minimum value. So this is going to be a min right there of negative. And when x is negative 1, we have a minimum. When x is equal to 1, we have a maximum, right? So then we keep going. We want to find now where we have where the function y is concave up and concave down. So we have to do the y double prime find that. So we find y double prime. Let's use, let's start with y prime equaling, let's use this form of y prime, x squared, debating here. Let's just go with this one, x squared plus 1 squared. So let's use that form of y prime. Sometimes, you know, we use one form of y prime to find the critical points for y prime, and then we use another form of y prime to then find y double prime. One's easier than another, so this will be easy enough for us to find y double prime. Let's do y double prime in green. So y double prime is the low d high, so low x squared plus 1 squared d high, so that's negative 2x, minus high, which is 1 minus x squared, times d low. Now, the derivative of this guy here is 2 times, I'm going to put 2 times what's inside, x squared plus 1 to the first power. Don't forget about multiplying by what's inside. So you're going to use the chain rule for this one. 2 times the quantity to the first power times the derivative of what's inside. And that's all over the denominator, x squared plus 1 squared, so that's x squared plus 1 to the fourth. So we're getting a little bit complicated here, but not too bad. Let's simplify the numerator by, let's do this first. Let's not multiply it out. Let's do x squared plus 1 squared there. And we have minus, let's go minus 4x times 1 minus x squared times x squared plus 1. And that's all over. Let's just do dot, dot, dot for the denominator there. Can we factor anything out? We could factor a negative 2x out, and we could also factor an x squared plus 1 out. And what that leaves is another x squared plus 1 there. And then we have plus, because we factored out a negative 2x, so we have plus 2 times 1 minus x squared. This just makes our lives a little bit easier, keeping track of the algebra here. And then let's simplify this a little bit more. Negative 2x times x squared plus 1, which will be a factor that's always positive. And then we have, I don't want to do too much here, x squared plus 1 plus 2 minus 2x squared all over dot, dot, dot. And then we have negative 2x, x squared plus 1. And then we have x squared minus 2x squared, that's negative x squared. And then we have a 3, so we have 3 minus x squared. Okay, all over, now we'll bring that denominator back in, x squared plus 1 to the fourth. So that's y double prime. Yeah, that is it's usually going to be more work than you normally will have to do here, but nevertheless, we know that y double prime. So the way we find our critical points for y double prime is the same way we found the critical points for y prime. We're going to set the second derivative equal to 0, and we do that. So second derivative equals 0 when either x equals 0 or 3 minus x squared is equal to 0. And so we get 3 equals x squared, x equals plus or minus radical 3. So if we take the square root of both sides, we're going to plus or minus radical 3. All right, now we need to do now our y double prime test. So our y double prime test. You know what, let's do that over here because we can relate that here to the y prime test. So we're going to do the y double prime test over here and the y double prime test. Now we have 3 critical points for y double prime. The first critical point is negative radical 3, and I'm gonna write these numbers down in relation to the y prime test. So we have y prime was equal to 0 at negative 1 and 1. Y double prime is equal to 0 at negative radical 3 and radical 3, which negative radical 3 is to the left of negative 1 or less than negative 1. Radical 3 is to the right of or greater than 1. And then 0 is right smack dab in the middle So y double prime equals 0 when x is 0. I'm going to do the rest of this problem in a second video.